Good evening, friends. Welcome to our Deep Dive Explainer. Today, we're going to get to the very heart of a crucial topic in strength of materials, the moment of inertia. Look, if you're gearing up for competitive exams like the TNPSC, SSC, or GATE, you already know that mastering this concept is non-negotiable. It's where the marks are. So let's break it all down, piece by piece, and truly master it together.
But before we jump in, a quick word on strategy, because I get a lot of questions about this. For anyone targeting the TNPSC syllabus, your main weapon should be the State Board Semicircle V books. But here's the trick, the real pro tip. Always, and I mean always, start with the higher standard books first. Think 11th and 12th grade material. Build that solid, high-level foundation. Then, if you have time, you can go back and review the lower grade books. Okay, strategy session over. Let's get into it.
So here's our game plan for today. We're going to start with the absolute essentials, the triangle formulas. Then we'll do a really deep dive on the semicircle. You'll see where every number comes from. After that, we'll roll up our sleeves and work through a full numerical example. And then we're going to answer the big question. Why does this thing even exist? Finally, we'll connect it all to the real world to understand what it actually means.
All right, let's jump right into section 1. We're starting with the shape that pops up everywhere in your exams, the simple triangle. Now, there are 3 key formulas for this shape that you absolutely, positively have to know by heart.
Here they are. These are the 3 standard formulas for a triangle's moment of inertia, where b is the base and h is the height. Now, about its base, the formula is a fixed value, bh cubed over 12. About its centroid, its center of gravity, it's bh cubed over 36. And about the apex, that top pointy bit, it's bh cubed over 4. These are standard fixed formula values. You just have to lock these into your brain.
Now, what's really cool is how these are all connected. You can actually prove one from the other using the Parallel Axis Theorem. You remember that one, right? It says the moment of inertia about any axis is just the moment of inertia about the centroid, plus this extra term, a times d squared. That's the area times the distance between the 2 axes, squared. Well, for a triangle, that distance d, from the base to the centroid, is a standard value of h thirds. If you plug that into the theorem, you can work backwards and prove that the centroidal value has to be bh cubed over 36. It all fits together.
And why am I stressing this so much? Because this isn't just theory. This was a direct question in the 2015 TNPSC Assistant Engineer exam. They literally asked for the moment of inertia of a triangle about its base. And here's the kicker. The correct answer, which you now know is the standard formula, bh cubed over 12, wasn't even listed in the options. See? Knowing these formulas cold gives you the power to spot errors and confidently secure your marks.
Okay, let's level up. We're moving on to a slightly trickier shape, the semicircle. But don't you worry, we're going to break this down so you understand exactly where its formulas come from, step by logical step.
First things first, how do we find the moment of inertia of a semicircle about its flat base? The logic here is actually super simple. We start with a standard formula we already know. The MOI of a full circle about its diameter is pi d to the 4th over 64. Now just picture it. A full circle is nothing more than 2 identical semicircles glued together at their bases. So it makes perfect sense that the total MOI of the circle is just the sum of its 2 semicircle halves. That means the MOI for one semicircle about that base has to be exactly half of the full circles.
So we just take the circle's formula, that pi d 4 over 64. We divide it by 2, and there we have it. This is a crucial calculated result. The moment of inertia of a semicircle about its base is pi d 4 over 128. Make a note of that one.
Okay, fantastic. That's the base sorted. But in engineering, the axis we almost always care about the most is the centroidal axis. So the million-dollar question is, how do we find the moment of inertia about the semicircle's own centroid? You guessed it, our good old friend, the Parallel Axis Theorem, comes to the rescue again. The theorem states, I base equals I centroid plus a times y bar squared. Now think about it. We just calculated I base, and the thing we want to find is I centroid, so we just need to rearrange the formula. To do that, we need 2 more standard formula values for a semicircle. Its area, a, which is pi d squared by 8, and the distance from the base up to the centroid, y bar, which has a fixed formula of 2d by 3 pi.
Now it's just a matter of plugging everything in.
I centroid is going to be our I base, which we know is pi d to the fourth over 128, and from that we subtract the area, pi d squared over 8, multiplied by the square of that centroid distance, 2d over 3 pi squared. Now, I won't bore you with all the algebra, but when you work through this and simplify it all down, it leads you to a very specific numerical answer.
And here is that calculated result. The centroidal moment of inertia for a semicircle is about 0.00685 d to the fourth. Now listen up. This is not just some random decimal. This exact numerical coefficient was a direct question on the TRB 2017 exam. This is why understanding how to derive it is so much more powerful than just trying to memorize a list of numbers. So let's put it all together. For the semicircle, these are the three values you need to lock in. About its horizontal base, the standard formula value is pi d to the fourth over 128. About its horizontal centroid, we have that calculated value of about 0.00685 d to the fourth. And about its vertical axis of symmetry, it's actually the same as the base, another standard value, pi d to the fourth over 128. These three are absolute gold for your exams.
Okay, memorizing formulas is one thing, but the real test is whether you can apply them. So let's put all this theory to work and tackle a full-blown numerical example.
But first, a quick word on circles and rings. For a solid circle, you know the standard centroidal MOI formula is pi d to the fourth over 64. Now, for a hollow ring or a pipe, the concept is beautifully simple. You just calculate the MOI for the big outer solid circle, and then you subtract the MOI of the empty hole in the middle. So the formula becomes pi over 64 times the big outer diameter to the power of 4 minus the little inner diameter to the power of 4. Easy, right?
All right, on to our main event. Picture a standard rectangular beam cross-section. We're going to use some assumed dimensions here, just for this example, okay? Let's say the width B is 120 millimeters, and the depth D is 200 millimeters. We're going to calculate three different things: the MOI about the horizontal x-axis, then the vertical y-axis, and finally about the very bottom edge of the rectangle, its base.
Okay, let's walk through these calculated results. First up, Ix. The standard formula is BD cubed over 12. We plug in our assumed dimensions, 120 times 200 cubed, all divided by 12, and we get a calculated result of 80 million millimeters fourth. Next, for Iy, the formula just swaps b and d, so it's dB cubed over 12. That gives us a much smaller calculated value of 28.8 million millimeters fourth. And finally, for the base, we use the parallel axis theorem again. It's our Ix value plus the area, which we calculated as 24,000, times the distance from the centroid to the base squared. For this example, that distance is an assumed 100 millimeters. This gives us a final calculated value of 320 million millimeters fourth.
So, we've gone through all these formulas, we've crunched the numbers, but it all begs a much bigger question. Why? Why are we doing all this? What's the real point of the moment of inertia? Why was it even invented?
Well, to understand the why, you have to go back in time to the early days of structural engineering. When the pioneers were first figuring out the mathematics of bending beams, they derived a formula that looked something like this. Now, the important part to see is that really messy integral at the end, the integral of y squared dA. It worked, but it was just awful to use. It meant that every single time you wanted to design a beam, you had to solve this complex integral from scratch.
And then, someone had a stroke of genius. They realized that this integral part, this integral of y squared dA, depended only on the cross-sectional shape. It had nothing to do with the material or the forces, just the geometry. So they said, hey, why don't we pre-calculate this value for all the common shapes and just give it a name? And that's exactly what they did. They called it I, and its proper technical name is the second moment of area. It's a pure property of a shape. And this is the payoff. By replacing that whole ugly integral with a single, simple letter I, that awkward, clunky formula transformed into the beautiful, elegant, simple bending equation that we all know and use today. The invention of I was all about making engineering simpler and more powerful.
So now we know what I is and why it exists. Let's look at where it shows up in the real world. This is where the rubber really meets the road in structural engineering.
In the entire field of strength of materials, moment of inertia is king in two massive areas. First, beam design. It's essential for calculating stresses and, critically, for figuring out how much a beam is going to sag or deflect under a load. And second, column design. I is what tells us the exact load at which a tall, skinny column will suddenly buckle and fail.
Just look at two of the most famous formulas in all of structural engineering. On the left, maximum deflection for a uniformly loaded beam. On the right, Euler's critical buckling load for a column. What do you see in both? That EI term. I, the moment of inertia, is sitting right there at the heart of both bending and buckling. It's simple. A bigger I means less deflection in a beam and a stronger column that can take more load before it fails.
Okay, so we've done the math, we've seen the applications, but let's get physical. What does I actually represent? What does it feel like? It all comes down to one word: resistance.
The absolute best way to get an intuitive feel for this is to grab a flat ruler. Seriously, if you have one nearby, grab it. Try to bend it across its thin dimension. It's super easy, right? It barely puts up a fight. That's because you're bending it about an axis with a very low moment of inertia. Now, turn that ruler 90 degrees and try to bend it the hard way against its deep side. It's incredibly stiff. You're now fighting against an axis with a very, very high moment of inertia. That physical struggle, that resistance you feel, that is moment of inertia in the real world.
And this brings us right back to our numerical example. It's not just a feeling, we proved it with math. Remember how we calculated IY, the easy way to bend, was only 28.8 million, and IX, the hard way to bend, was 80 million? The number for IX is nearly 3 times bigger. The math perfectly explains what you feel with the ruler. The rectangle is much, much stiffer about its strong x-axis because its moment of inertia about that axis is so much higher.
So if you remember only one single thing from our entire session today, let it be this. The greater the moment of inertia, the greater the resistance to bending. That is the fundamental concept. It is the most important property of the shape that tells us how stiff a beam will be. If you can truly master this concept, you are well on your way to mastering beam design.
And that's a wrap on our deep dive into the moment of inertia. Keep practicing these problems, keep reviewing these derivations, stay focused on that goal, and I promise you, you will achieve it. If this explainer helped clear things up for you, make sure you subscribe for more sessions designed to help you ace those exams. All the best with your studies.